7, which is basically what I stated here. In this chapter, we will solve problems by applying a set of procedures, not by memorizing a set of equations. And this goes back to what I want to stress here. I know that with the kinematics chapters, it seems like we were just applying equations over and over and over again. And maybe just applying equations, not so much conceptual understanding. Well, as we start to study forces, I think the level of conceptual understanding that's required increases. And I'm hoping that will be more of an emphasis from this point forward. So, the topics in Chapter 6. We'll spend pretty much all today talking about the first one, which is equilibrium. From there, it goes on to applying Newton's second law, discussion of mass, weight, and gravity, then friction, drag, and then the textbook supplies a lot of other examples of Newton's second law. So, our topic for today is equilibrium, and we discussed this a little bit in Chapter 5, which I know I only spent one lecture on Chapter 5, but this was one of the topics that was mentioned. When we're talking about equilibrium, we're talking about a situation where the net force on an object is 0. And we remember that there are two different kinds of equilibrium. We can have static equilibrium, where our object is not moving at all, our object is at rest. Or we can have dynamic equilibrium, where our object is moving at a constant rate, a constant velocity, constant speed. In both these situations, the net force on the object is 0. But basically, this is just the idea of equilibrium. Two different kinds, static or stationary, and dynamic equilibrium. And the last sentence here makes the point that both of these equilibriums are identical from a Newtonian perspective, because the net force and acceleration are 0 for both static and dynamic equilibriums. So we can take a look at our problem-solving strategies when we're dealing with equilibrium problems. First, of course, is to come up with some kind of model for our problem, making simplifying assumptions and representing our object as a particle. We draw out some kind of pictorial diagram. So we do this by establishing a coordinate system, defining our symbols, and identifying what the problem's asking for. We draw a picture identifying all the forces acting on our object, and then we show those forces on a free body diagram. And this free body diagram here is something that I'm going to expect on every single problem that involves forces. You should always have a free body diagram on your problems. All these elements, as it says, form our pictorial representation of our problems. And then when we're talking about specifically equilibrium, we're talking about the situation where the net force is 0, the acceleration is 0, and this is just Newton's first law. So after the pictorial representation, we move on to our mathematical representation using Newton's first law. And Newton's first law states that the sum of our forces is 0. And we can look at the consequences of Newton's first law. And the last point here is that our vector sum of our forces are found directly from our free body diagram. And that's something that we'll see as we go through a few examples here. sum of the forces is equal to 0. Okay? I'm going to take a look at the end of chapter problem number 3. In this problem, we've got a 20-kilogram loudspeaker that's suspended 2 meters below the ceiling by 2 3-meter long cables that are hanging at equal angles. And it asks, what is the tension in the cables? So this is the end of chapter problem number 3. We've got a 20-kilogram loudspeaker. It's supported by 2 cables at equal angles. So this is hanging from the ceiling. So the question is, what is the tension in the cables? And just to make this a little more concrete for you, this is the basic situation that we have here, where we've got a loudspeaker hanging suspended from 2 cables that are attached to the ceiling. And those are at the same angle. The length of our cables is 3 meters. And the box is hanging 2 meters below the ceiling. So, what should I do from here? What's that? Yeah, draw a free body diagram, certainly. So to draw a free body diagram, I represent my loudspeaker just as a particle. And then I draw out all the various forces on it. So if you remember from chapter 5, we said that the first thing we want to do is look at our contact points for our box. In this particular instance, we've got 2 contact points here. Basically cable 1 and cable 2. So we can draw out the forces due to our contact points here. Cable 1 and cable 2. I'm going to label those with labels T1 and T2. T is tension. So that's all our contact points. The last step in drawing these free body diagrams is to look at our long-range forces. In this instance, our only long-range force, of course, is the force due to gravity. So I've got my free body diagram drawn out here, and I probably should go ahead and put my angles in here again. Again, we want one of these on every single one of these force problems, free body diagram. Let's see, I need to write out the principles that I'm going to use to solve this problem. What are some things that I could write down for this? Newton's first law, sure. What are some? Is there another possibility as well? I mean, it's basically another way of stating Newton's first law. Equilibrium, yeah. What kind of equilibrium in this case? Static, yes, absolutely. So things that I could write here: static equilibrium, Newton's first law, and also I can write down that I'm going to use the principle of superposition. And I'm looking for some subset of these principles on your homework, you know, in your exams. If you don't get, you know, every single one that I've written down here, I'm not all that incredibly concerned about it. I just want to see that some thought has taken place here as to what principles you're using to solve the problem. So, for instance, you know, on this one, I could have possibly just written down static equilibrium, or I possibly could have just written down Newton's first law, and I wouldn't have a problem with that. I'd be fine with that. Let's see, what else do I need to do here? What's that? One more time.
Find the angle.
Find the angle. Yeah, I do need to find the angle. So that would be one of my knowns for this problem, right? Or at least something that I could solve for that could become a known. Yeah. So my list of knowns for right now, my mass is 20 kilograms. I could possibly put theta down here because it's kind of straightforward to find it, and then I want to find my tension. So let's go ahead and take a look at that theta. Here we said that the height is 2 meters, and the length of the cables is 3 meters. So how do I solve for this angle theta? So cosine theta equals adjacent over hypotenuse. So my adjacent in this case is 2 meters. My hypotenuse is 3 meters. So my theta is equal to, I'll just go ahead and write out 2/3. My theta is arc cosine of 2/3. And I'm just going to leave it at that. And not write down an angle. The angle's 48 degrees, but turns out we don't really need it. We do need it, but not in that form. Okay. So I've gotten this far. I've figured out this angle. I've kind of got my problem set up. What do I do from here? This next step is probably the key step in a lot of these problems. Any suggestions? That is something I need to do. That's not the one I was thinking of, but yeah, that's absolutely a valid thing that I need to do. You said calculate the force due to gravity. And we'll definitely get there. Looking for something else first, though. Equations. What do you mean equations?
I guess in this case, since nothing's moving, we know the net force is 0.
Okay.
So that has to be the vector sum of all the forces acting on.
Okay. Okay. You're almost there. You're almost where what I'm digging for. So what I'm digging for exactly is we want to break our forces down into x and y components. If this thing is at static equilibrium, if this thing is at equilibrium, it means that the sum of my forces in x and the sum of my forces in y both have to be 0. So my strategy on this and on pretty much all of it, we need to break forces into x and y components and then analyze the sum of my forces in my x direction is equal to 0, and the sum of my forces in my y direction is equal to 0. So break down my problem into x and y components. So let's see, my force due to gravity just acts in the y direction. For the sake of completeness, I probably should have written up here somewhere a coordinate system, x and y. My tension forces, on the other hand, have both x and y components, so we need to go about breaking down my tension into x and y components. So let's look at T1. Got our angle theta here. This is T1y. This is T1x. Okay, now what? How do I solve for T1x? What do I write down? Yeah, is it cosine? Yeah. When I'm looking at x here, T1x, this is going to be, let me just sort of be very specific that I'm talking about magnitudes. This is going to be sine theta in this instance. My T1x, as I've got it drawn out there, is opposite my angle theta, so I have to use sine. Okay, my T1y, of course this is cosine theta. I can do a similar analysis for T2. My T2x is going to be T2 sine theta, and my T2y is going to be T2 cosine theta. Okay, so now that I've gotten those broken down, I can actually take a look at my Newton's first law equations. So my sum of my forces in my x direction is equal to 0. The sum of my forces in my y direction is equal to 0. So now I just need to make a listing of those forces in my x and y directions. So we take a look at the forces in the x direction. Well, my force due to gravity just points straight downwards. I've got x components in my T1 and my T2, so I need to write these out. The sum of my forces in my x direction is equal to T1x plus T2x, and this is equal to 0. Well, let's write out what T1x is. If we look over here at our diagram, we see that T1x points to the left. It points in the negative direction. So, sum of my forces in the x direction is equal to negative, and then my T1x is T1 sine theta. If I look at my T2, we see that my T2, it points to the right. So it points in the positive x direction. So this is plus T2 sine of theta equals to 0. So we can do a little bit with this equation. We see here that both terms have sine theta, so we can divide through by sine theta, and we can rearrange this a little bit. When we do this, we get that the tension of 1 is just equal to the tension in 2. Okay, well that makes sense. They're at the same angle. It makes sense that they would have the same tension in them. So we've gone as far as we can go with that. Let's look at the sum of my forces in the y direction. Can you guys read that back there? Barely? Okay. Thank you for telling me. So let's look at the sum of my forces in my y direction. This is equal to 0.